All right, let's do this. Logistic regression intuition. And you can probably already tell by my voice that I'm pretty excited. There's some very interesting slides coming up, and this is quite an important topic. But at the same time, it is quite challenging. So a quick heads up, there will be some math, and I've done a few run-throughs of this presentation already, and I will try my best to convey everything in the simplest way possible. So let's get into it. We already know about the linear regression. We know that there's a simple linear regression and it has this very short formula with one independent variable. And we also have looked into the multiple linear regression, which has many independent variables. So we already know how to deal with this type of challenge. So when we have a scatter plot like that, where on the horizontal axis, we've got the independent variable. On the vertical axis, we've got the dependent variable. And this is an example we looked at: salary versus experience. How do we create a model here? So we use a simple linear regression. It puts a line through our data, and that line is modeling our observations. So we can basically forecast things and compare our actual observations to our model and so on. So we know how to deal with challenges like that or problems like that. But your company that hired you as a data scientist, what they do is they send out email offers to customers with like a proposal to buy certain products. It might be a clothing store, it might be a grocery store or something like that. So what they do is basically they send out a offer in email to a lot of customers to purchase certain product. And here you've got a sample of those customers that they contacted recently. You've got their age, and also you have a variable whether or not they took action. So did the person take up an action, perform an action? Did they take up an offer? Did they buy a product? Did they open up an email, respond to our email, and so on? So was the action taken or not? And very black and white, very different. But at the same time, like, even though we don't know what to do, we don't know what's going on here, it's not what we're expecting. But at the same time, intuitively, we can see that there is some sort of correlation. We can see that the observations on the bottom, they're a bit more to the left, observations on the top are a bit more to the right, implying kind of that probably older people are more likely to take action based on this offer, and younger people are more likely to ignore it. So can we somehow model this? How about we try the existing method in our toolkit, which is the linear regression. Let's run a linear regression, and that's what it looks like. As you can tell, it doesn't look like the best approach. It doesn't look like the best method to solve this problem. So let's look into this in a bit more detail. We're going to draw the other horizontal line over here. Instead of trying to predict exactly what's going to happen for any given person, let's imagine a person, and let's say we want to predict for that person, knowing their age, we want to predict whether they will take up the offer or not. But instead of predicting exactly whether they're going to take it up or not, how about instead we will predict the probability. We will state a probability or a likelihood of that person taking up that offer. And if you think of it in that way, right away things start becoming clearer. Right away you can see that, okay, so this chart is actually from 0 to 1. And I also know that probabilities are from 0 to 1. Oh, that's interesting. So basically I could fit in probabilities between 0 and 1. The fact that the red dots, the red observations are already either 0 or 1 and nowhere in between, well, that's simply because we already know the result. We already know that they're either there or there. But for something that we're predicting, it kind of makes sense to say, well, I don't know for sure, I don't know 100% he'll take it up or not, but I know maybe with an 80% chance he'll take it up or not, right? And when you think of it that way, the linear regression line, or at least that part that's in the middle between 0 and 1, it makes sense, right? Well, it makes some sense, because that is basically, it's telling you that anybody between those ages of, for instance, where it's crossing the horizontal line for the first time, it might be, or where it's crossing the horizontal axis, it might be like 25, or let's say 35. And where it's crossing the horizontal axis for 1, it might be, let's say 55. So those people between 35 and 55, they anything in between, any person that falls in between that age, there is a probability of them taking up this offer, and that probability is increasing as we move to the right. As we take more and more older people, that probability is increasing. So the part of the linear regression in the middle kind of makes sense, and we can do something with it. But the parts that don't make sense at all are the ones at the top and at the bottom, because a probability can never be less than 0. It can never be above 1. So what is the linear regression trying to give us a hint about here? Well, what it's probably saying, what we could interpret it as, is that people above that age, that nominal age, we said 55, above that age, they are very, very likely to take the offer, actually more than 100%. So basically, they're definitely taking it up. Anybody below 35 on the other side, on the left, they're definitely not taking it. So essentially what we're saying is, if we ever take that approach, then we would have to replace this linear regression line with a line that looks like that. So let's just cut those bits off and replace them with horizontal parts. And that would be a very basic, but it still would be an attempt at creating a model for this situation. So we would still be able to use this to make some sort of predictions and assumptions that talk about the correlation between the action and the age of a person. So that's a very basic understanding, and that's kind of the start of our understanding of intuition behind logistic regression. So let's see what the actual scientific approach is. So here we've got the line that we looked at, and it is described by this equation. Now this part is going to be, this is the most fun part, so bear with me. If you apply to this equation a sigmoid function, which looks like that, so you put the y into the sigmoid function in purple, and then you solve for y from the purple box and you put y back into the blue box, then you will get the green box. So basically, your linear regression will start to look like this. And this is the formula for logistic regression. And what that will do to a chart, which is most importantly this visual part, it will convert it from the chart that we see at the top to this new chart, which is actually the logistic regression function. So if at this stage you're asking yourself what just happened, then you're not alone. The first time I saw this, or I learned this was the expression on my face. If you're totally comfortable with all of that, that's super great. That means you'll fly through this section. But if you're confused right now, not a problem. I was the same when I was in your shoes. So let's take this step by step. Let's look at it step by step, exactly what happened. So there's our graph. There's our independent variable. There's our outcome, yes or no. So that's the y, the dependent variable. And there are our observations in our data set. Based on these observations, and plus using this formula, which we're going to take as given, this is the logistic regression formula. Using this formula and these observations, we come up with this line. And what is important to understand here, it's not a magical line. This line for the logistic regression is the same as a slope or a trend line for a linear regression. So basically what this line is doing is it is using the formula, it's following the formula, and it's the best fitting line that can fit these data sets. So basically we're doing exactly the same thing as with a linear regression, but it just looks different. That's all. So there are heaps of these lines that you can draw that look like that, but only one of them is the best fitting line. So the point of the logistic regression is to find that best fitting line. And this is it. So we found the best fitting line that follows that equation and fits these variables or these observations that we had in our data set. After that, we can forget about the equation, we forget about the variables. We've got our line. So this is our logistic regression function. We've found it. Same thing as with the linear regression. We've created the model. We've built the model. You can see it. This is the model in front of you right there. Now, what can we do with this logistic regression? Well, we can use it to predict probabilities. And we've already touched on probabilities, that they lie between 0 and 1, and that instead of predicting for sure that something will or will not happen, how about we predict probability? So let's look at, oh, by the way, probability here is called p hat. So that's a little sign above the p gives it the name p hat. And anything you see in the with a hat in this section just basically means that it's a something we're predicting. So and that's a way to remember it, that picture p hat. So we're predicting this probability. Okay, so let's take 4 random values for the independent variable. For x, we're going to say 20, 30, 40, 50. Let's see what happens to these variables. So let's put them on the x line. Those are the dots. And I specifically put dots, not x's or crosses, because it doesn't mean that they're on the horizontal, the bottom line doesn't mean that their probability is 0 or that their dependent variable is 0. No, they're just there because they're on the x-axis. We just plotted them there. It has nothing to do with the vertical axis. Now, what you need to do to find the probabilities is you need to project these values onto your curve. Once you project them, you get these blue dots or blue observations, which plotted basically. So these are the fitted values. As you remember, in Gretel, you have in red you have the actual, and in blue you have the fitted values. So these are your fitted values. And now, if you project them, if you want the probabilities, you need to project them to the left, like that. And let's have a look at these probabilities. So the person who's 20 years old, the probability of taking up this offer is very low, perhaps 0.7%, so less than 1% to take up this offer. The person who's 30 years old, the probability is higher. It's about 23% to take up this offer. The person who's 40 years old, their probability to take up this offer is 85% according to this model. And the person who's 50 years old, their probability is 99.4%. So that's the first thing that you can get out of a logistic regression. That's what we're going to be using we're going to be using it very actively when we're talking about building geodemographic segmentations, because you use this probability as a score, and I will talk about this more. So you can actually rank people, who is the most likeliest to take up your offer and who's the least likeliest to take your offer up. So it's actually even better than just having a 1 or a 0. You have a probability, so you can order people by this probability. Anyway, you might want to say, well, I don't want the probability. I want a prediction as because this is a regression. I want a prediction for the y value. So, okay, we can do that. Can we get, let's get rid of those probabilities. Now, can we get the actual? Well, obviously we can't get the actual because the actual is something that we can only observe in our data set or in real life. We can only get a prediction for the actual. So y hat, as the hat suggests, is the predicted value for the dependent variable. How do you get y hat? Well, the approach is very arbitrary. You have to select a line. Let's wait for that. Okay. So you have to select a line. In this case, we're going to select 50%. You can select it anywhere, but 50% is usually selected because it's in the middle and therefore you have symmetry. And anything below this line, so anything that falls on the curve below this line will be projected downwards onto the 0 line, which makes sense. So it's basically saying if your predicted probability of taking up this offer is less than 50%, let's say it's 40% or 20%, then we're just going to say that you're probably not going to take up this offer. And so that's what's happening. The person with 0.7%, the person with whatever it was, 27%, 23%, their probabilities are not 0, but they're below 50. So if you do require a y hat, so a predicted value, a yes/no value, then makes sense that if something's below 50%, you're probably going to say that they're not going to take up the offer. Now, anything so there you go. Both of them, y hats are 0. Now, anything above the horizontal line that we've selected, the 50% line, it is agreed that all of those values that fall onto the curve above that line are projected upwards. They're projected onto the yes line, the 1 line. So the person that had a probability of 85% is projected upwards, and the person that had the probability of 99.7% is projected upwards. Also makes sense, right? So if somebody's got a chance, you're predicting that somebody's probability of taking up an offer is 85%, then if you have to say yes or no, then you're probably going to say yes. You're going to say yes, this person will take up the offer if you have to choose one of the two. So those are our predicted y hat values. In this case, they're both 1 for those two variables. And those are the two things you can get out of the logistic regression. So you get the probabilities, which are important. Also, you can get the y hats, so the predicted values for the dependent variables. Once again, it's important to think of it as it's doing exactly the same thing as a linear regression. It's fitting this line, even though it's not a straight line, and the values are not scattered. Everything looks bizarre in its uniformity, or in the way in its structure makes it look very bizarre. But still, it's pretty much the same way. We've agreed on a line or a formula for a curve, and we're trying to fit the best curve to our data. Once we've done that, we've got a model, we've got the coefficients, which we'll talk about later, and we can start drawing conclusions or insights from this model. And some of the insights are we can get a probability of somebody taking action or of the event occurring, and or basically of the answer being yes. So it's not a yes no, it's a probability. So 85% or 20% or whatever. So that's when we project it to the left onto the y-axis. And also we can get a predicted value for the dependent variable based on where we select this arbitrary line, 50%. You can select it anywhere you like. You can select it higher, lower. Depends on your knowledge about the problem at hand. And as you understand, depending on where you select it, that will significantly affect your variables. So I really hope this explanation was trivial enough and yet insightful enough for you to gain an intuitive understanding of logistic regression. I look forward to seeing you then, and until next time, happy analyzing.